Okay, so in this lesson we're going to look at solving for the electric field, which is given by some charge distribution. In this particular example we're going to consider a circular ring of radius A. The ring lies in the xy plane and it carries a non-uniform line charge which is given by lambda equal to A sine phi. And phi is the usual cylindrical coordinates, it's our azimuthal angle, and A is a constant. And what we want to do is calculate the electric field at some point P, which is located at 0, 0, Z. Okay, so the first thing that we want to do is just write down what is the equation for an electric field here. So here we have E. Integral. We have here is lambda, which is our line charge, R prime to be squared. Write down a unit vector, which is R minus R prime. And it's dl prime. Now remember again, we have the prime here. This is very important. We have the prime here because the electric field will depend on the source. It's going to change in direction, and the direction is given by the source. Okay, so this is our equation. Now what we want to do is write down what our source and our field vectors are. Okay, so for our field vector, which is given by R, well, this is going to be equal to z hat. Remember, it's that distance away from the origin. It's in the z hat direction. So it's z hat. So now what's R prime going to be equal to? Okay, so for our source, R prime will be equal to S hat, where S is equal to A. Okay, so we have S hat, which is equal to A S hat. Okay, where A is just the radius of our ring. Okay, so now we can basically write down the rest of the equations. We can write down our separation vector now, which is going to be R minus R prime, which is given by Z hat, minus A S hat. And our unit vector can be Z hat minus A S hat over square root of Z squared plus A squared. Now, the other important bit of information that we require here is the infinitesimal displacement element, which is dl prime. Well, here we have dl prime, so S is constant, Z is going to be at 0, so dl prime is going to be equal to S d phi prime, which is equal to A, okay, it's equal to A d phi prime. Okay, and we're going to have to integrate this between 0 and 2 pi. Okay, so now we have all the information that we require. What we have to do now is just to plug everything into this equation, okay, and then to solve it. So let's just do that. Okay, so we have our electric field equal to 1 over 4 pi epsilon naught. Lambda or prime is given by a sine phi, so we got the integral from 0 to 2 pi. We're integrating with respect to phi, okay, our azimuthal angle. This is a sine phi over square root of z squared plus a squared, all to be squared. Then our unit vector, so we have z hat minus a s hat square root of a squared plus z squared. And here we have a d phi prime. Okay, we're integrating with respect to phi prime. Now, what's important here to realize is that the s hat cannot be taken outside the integral. The reason being is the s hat is going to be changing in direction as we do our integration. Okay, so what we must do is convert the s hat into Cartesian coordinates. Okay, so s hat, and you can find this in Griffiths, is going to be equal to cos phi x hat plus sine phi y hat. Okay, now we stick this back into our equation instead of the s hat, and therefore what we will have is our electric field between 0 and 2 pi of a sine phi all over z squared plus a squared to the power of 3 over 2 z hat minus a cos phi x hat minus a sine phi y hat by a d phi prime. Okay, so now what we have are three integrals that we can solve. We've got an integral for the z hat term, we've got an integral for the x hat, and we also have an integral for the y hat. And now because these are constant in direction, they can be taken outside the integral. So now if we solve this, if we look at the integral with respect to the z hat, so we have the Ez by a well, the integral of sine phi between 0 and 2 pi results in 0. Okay, so our Ez component is equal to 0. Now let's look at our Ex component. So we have our Ex And this is going to be given by big A squared, sine phi cos phi, three over two, and this is d phi prime. Now taking the integral of sine phi cos phi between 0 and 2 pi for phi results in 0. And now if we look at our EY component, this is going to be a sine squared phi all over 3 over 2 d phi prime, and the integral of sine squared phi between 0 and 2 pi results in pi. So now what we have is over 4 pi epsilon naught a squared by pi over 2. Okay, so a final answer for our electric field . Over 4 pi epsilon naught. In fact, we'll cancel the pi's here. Okay. Of course, this should be a negative. Okay, these are negatives in here. It's a negative. Okay, because you have a minus a sine phi y hat over here. So it's minus 1 over 4 epsilon naught a squared over the y hat direction. Okay, so that's our solution to the electric field for that circular line charge.